recap some of the ideas of dispersion, because it's not something that we spend a lot of time when we're talking about the electromagnetic spectrum. So just to remind you, dispersion is the effect that happens when white light passes through a prism. Now you'll see here in this simulation, I'm started off here actually with non-white light. And this is what we'd call monochromatic light. Now monochromatic light is mono, one, chromatic color light. And the color is actually dictated, well, you can look at it two ways. It's dictated by the wavelength. Well, if we're changing the wavelength, then we're actually changing the frequency as well. So monochromatic light, just to be clear, is light with a particular frequency or a particular wavelength. And there's only one particular frequency within that beam of light. Okay, we're not worried about amplitude or anything like that. All right. You should have seen there when I changed the wavelength of this light that my low wavelengths, so high frequencies, are deviated a lot, whereas our high wavelengths, slightly lower frequencies, are deviated much less. Okay, and if we just sort of flick between the two, you can see that a bit more clearly. Okay, now obviously, as we said, this idea of dispersion is about what happens when white light comes through, and you can see that quite clearly here. Okay, we've passed our white light through the prism, and we're seeing there that we get this kind of rainbow effect. Okay, let's just sort of rotate this guy around. I'm trying to make it a bit clearer. One thing that you will be expected to remember in your exams is simply kind of the order of these colors and the fact that red is at the top. Red is the color which is deviated the least. And blue, we tend to think about blue, we tend to kind of ignore the violet stuff because that's getting into ultraviolet. That is the one which is deviated the most. So we're looking at light with a large wavelength, so high wavelength, that's red, being deviated the least. And then our lower wavelengths, higher frequency being deviated the most. Okay. Now, it's quite sort of advanced physics, but I thought it would be worthwhile looking at why this is the case. And for this, I'm going to actually switch tabs here. Okay, we're looking here at exactly the same material. Okay, this is air into glass. Now, unfortunately, unless I've missed something, I cannot put white light into this. But what we can look at is the monochromatic light and sort of see what's happening here. But this is just our classic refraction. Okay, we've got in this case, violet light coming in, okay, and then it's being refracted as it passes through the glass. Now, the bit I wanted to demonstrate is really to do with the speed. Okay, if I go from our, in this case, low wavelength up to my high wavelength, okay, what you hopefully will notice is actually something kind of interesting happens. Again, we'll go the other way. That number 0.66c represents the speed, as it says below. You're noticing actually that these waves don't quite have the same speed inside our material, and actually that is what affects their angle of refraction. Dispersion, this effect happens because we have refraction at each stage. We've got refraction when we go in and out. Okay, so what you're noticing here, okay, is that actually these rays of light, when they meet, imagining if they're inside white light, they meet the prism, they all are refracted by slightly different amounts, okay? In the case of purple, that's got an angle of incidence, a lower angle of incidence than red. It's not very much, okay? Purple has an angle of incidence of 27.8, and, an angle of refraction, I should say, of 27.8, and then we've got an angle of refraction of 28.2. Okay, and that is really the level of splitting that we get. So this is why we don't really observe this that much in real life. The splitting isn't very great. Okay, now if you follow over here, instead of looking at the speed, that's to do with the speed change, you'll notice something else changes. If we go from our low wavelength to our high wavelength, actually notice that the refractive index is slightly different. This isn't a fault of the computer or of the simulation, it's actually what the reality of the situation. The reason that dispersion happens is because different wavelengths or different frequencies of light have a different refractive index in a medium. Okay, so if we say that the refractive index of glass is 1.5, which is usually the case, okay, actually what we're saying is kind of on average. But really, for different colors of light, they have a slightly different refractive index. The result of this is that those low wavelengths, like blue and purple, they will travel slightly more slowly than, say, the red. Okay, and that is why they have slightly different angles of refraction, and that's why we get this beautiful effect, which is the dispersion of light, i.e. the production of that kind of rainbow. All right. So as I've said, at GCSE level, I don't think this is something you really should get worried about. I have just noticed a few questions which are just sort of like picking up on dispersion. I don't want anybody to feel unprepared. Okay. Key idea being that dispersion is due to refraction, and we've got our refractive index slightly different for the different wavelengths or different frequencies, different colors, and that is what's causing them to travel at slightly different speeds. To be clear, low wavelengths, blue, etc., are slightly slower than high wavelengths, red, and that's what's causing our dispersion. Hope that's clear, and as ever, please let me know if there's anything I can do to help make that even clearer. Thanks for watching.